So now we are going to start to prepare, characterize the optimal mechanism, because the question is the mechanism we had been considering proportional allocation already from on the second lesson, and also now, is it like better than all the other mechanisms, some other mechanisms, or is it just a nice mechanism that we chosen, and luckily it turned out to be good. So now we're going to characterize all the mechanisms which are good, so to speak, or basically speaking, we're going to look into the structure of the mechanisms which are good. So we need to define what are the mechanisms to look at, and so on. What do we mean by being good? So now we are going to actually prepare the formal ground for this definition. So in the question is the mechanism that we are considering, the proportional allocation mechanism, desirable among a certain class of mechanisms. Because you cannot look at all the possible mechanisms, of course. If you do, even if you try to define it, probably will not be interesting, because even if there will be better mechanisms, they won't be realizable. Probably you can always find the mechanism price of anarchy one, as I once mentioned in some other context. You can just tell that if you do this what I want, and I don't do anything, or I give you a lot of whatever, a lot of utility, and otherwise I fine you strictly, but of severely fine you. But of course, it's not practical, and we don't want to do it, and so on and so forth. And so we do need to define a certain class of mechanisms, which is practically reasonable. Also, sometimes we want to have some basic assumptions for the sake of theoretical analysis. So, a desirable mechanism will be defined basically. A desirable mechanism will be defined as minimizing the efficiency loss, pretty much the price of stability or price of energy. So, in the case of price anticipating the users, uh, the price of stability was equal to the price of energy. And desirable mechanisms uh, are minimizing efficiency loss for price anticipating users, and regardless the utility functions which each user may have. That's what we call desirable mechanisms. And of course, we also require, as I already mentioned, the strategy space. So all the possible ways to beat it's a low dimensional thing. In our case, this is scalar and non-negative real number. Now, there is some important emphasis that the valuations are not assumed to be somehow low dimensional. The important part is that communication needs to be low dimensional. So I may only communicate a non-negative real color. I mean, a player may only communicate that. I'm not telling that that's the evaluation, but let's see what we assume. So let's wait for the formal definitions. The important part is that the communication is response column, and we'll prove that under some assumptions, including like just technical, but not only technical assumptions, the proportional allocation mechanism that we have considered actually minimizes the worst case efficiency loss. Basically, the price of anarchy, that's the worst case efficiency loss, that's minimized by the proportional allocation. By the way, note that worst case is basically a very computer science approach. And what we are doing now, game theory, is something which we might assume, why not have an economic approach? Why not look at the average? Especially if we have some prior distribution in mind. The answer is, even if we have a prior distribution, it's extremely hard to analyze such a model. But there are such models, but it's extremely hard to analyze them. So we are going to look at worst case. And we recall Thus, that the set of all the value functions is that something needs to be true regardless of utility functions. So the set of all the value functions, the functions that define how much a certain piece of a resource, a certain part of resource is valued, this has to fulfill certain assumptions, pretty much technical ones. So each value function is concave, strictly increasing. So the more resources, the better, strictly better, and continuous over non-negative reals. Each value function is also continuously differentiable over the positive reals, so it means it's differentiable and the derivative is continuous as the function, and the derivative from right is zero this and is final. And the set of all such functions of all the possible value functions will denote that it's as we have denoted that also as a calligraphic V. Now we always work in the environment. Now basically we formalize and in a way generalize things we have been in a way implicitly assuming till now. So we consider the environment of C, R, and vector V. C being the resource capacity, which is divided. The users, and it can be divided arbitrarily. The users are 1, 2 till R are being a real, an integer number or a natural number strictly greater than 1. And the utility functions, that's the vector v for each use. There is a utility function, each function being from this calligraphic v, which I've defined. First, the definition of a market clearing mechanism. Again, a generalization of what we've been looking. It's basically a differentiable function which will play the role of a demand function. So, given two integers, one positive, the other one non-negative, it returns a non-negative integer such that basically it takes the price, it takes my that agent bit, and it returns how much the agent gets given the bit and given the price. Because the price might be the function of the bit, but let's go. It will be actually a function of the bit. So that's what we require is that for any size of the resource we are dividing for any number of players greater than 1, and for any vector of bits, negative reals, which is not a zero vector, there exists a unique price, a unique positive price, such that the total demand under this price and bits will be C. So basically, a market clearing mechanism is a demand function such that for any resource being divided for any number of players and for any bit, there exists a unique price such that total demand will be exactly the resource we are dividing. So the market will exactly be cleared under these prices. And we denote this unique price by P d theta. It may depend on C. Which is not denoted, but may depend on C. Actually, it does for the example for the case of the mechanism you just showed. So first of all, well, let me just mention that the mechanism, I think we are going to show it later, but the mechanism of proportional allocation is such a mechanism. So the demand function is basically the bit divided by the price, and this condition that the sum of the demand is exactly the supply C basically means that the price has to be the total bit, the sum of the bits divided by C. And that's exactly what we did. So for theta being the zero vector, the prices are undefined. And when defining a game, then we just define the utility of the players are just minus infinity. That's not what we did before. Before we just told that the utility of the players is the value of not getting anything because the players didn't get anything. When it was zero minus paying zero. So it was usually zero. Anyhow, it was value of not getting anything minus paying zero. Here we define it minus infinity. It's a bit different. It doesn't affect the characterization below, but we'll talk about it, I think, a bit more. So this is, as I said, generalized element function approach. So there, the user bits theta, and this is the main function. So how much basically you can get under the price. The price is one for everyone in this model. Anyhow, so you tell how much you would like to pay, and dividing that by a price determines how much you demand. The mechanism chooses the price, the unique price such that the total demand is equal to supply, the C, I mean. And then the price is exactly the total bid divided by C, unless we choose a vector of zeros, as we said. And let's now generalize notions of competitive equilibrium and Nash equilibrium. So a competitive equilibrium is generalized as follows. Given a utility system, I remind that it's simply the divided resource, the number of players, and the vector of the values, and a smooth market clearing mechanism, which is that function D, a vector of bits non of zero is a competitive equilibrium for mu, the price mu, if if for the price mu under this equilibrium, the personal utility is optimized when the mu already is fixed. Then, so now let's compare. Here the mu is fixed, and I just look how much I get given my bit under this mu. What is my utility? What is my value of what I get? Minus how much I pay for the amount I get under again this mu. Now, and I would like to get a maximum, a best possible thing under this assumption. Now, given a utility system and a smooth market clearing mechanism, be a vector of bits which is not zero, not a zero vector, is in a Nash equilibrium if simply that's the best response. So what we want to hear is that for any player and for any bit player, the utility of the player is maximum possible given what are those bits, where the utility is defined to be the value of what I get minus what I pay, when the price is also dependent on what I do. So I compare in both cases, and otherwise, if the vector is 0 is minus infinity. Not getting, so having the theta 0 is worse, is infinitely worse for everyone. Now, just some clarification. The price mu is determined exactly as the price in the case of Nash equilibrium is determined. In the case of competitive equilibrium, the price is determined exactly as it's determined in the Nash equilibrium. But having determined that, we just want to have a best theta r, given that that already has been determined. So we don't compare, well, excuse me, when we compare theta r to other theta, actually that should be theta bar, not, well, this bar is not the right one. Okay, okay, 1 second, please. bar should not be inequality, but only of theta r. I should now very better. So in both cases, the price is determined by the theta. But the optimality is determined when we compare what we have for various theta r's. And when I look at other theta r's, I assume that it does not change the view. Whereas here, in the case of Nash equilibrium, where I look at other theta r's, theta r bars, I assume that it does influence the view. That's the view. Okay, now let's. Okay, so we have generalized the equilibrium, and finally, we generalize the mechanisms we consider. So we consider the following mechanism. I remind you that T theta is a demand function, and plus calligraphic D, which contains all the calligraphic functions that we consider, is defined as follows. First of all, each calligraphic function is a smooth market. Each demand function is a smooth market clearing mechanism, as defined before. Then some other properties. So for each side of the resource divided, for each variation of a player, a price anticipating user pair is concave. Namely, for any number of players and for any bits of the others, the function of what I get, my value for what I get minus what I pay for what I get, is concave in my bit on the domain of all the strictly positive reals if the other bits are not all zero, and on the domain of all zero, because then I may not be zero. I may, but if I be zero, I remind you that it will eventually cause everyone to get minus infinity, and I don't care. I don't require concavity in this domain, so therefore I don't require concavity of zero when that is bit vector zero. And if that is bit not the vector zero, then I may also reasonably be zero. So my requirements for concavity includes the point zero. Then for any price, positive price, for any non-negative demand, there exists some bit such that the bit the demand under this price will be exactly equal to the demand. Kind of onto requirement. Another requirement is for any positive price and non-negative bit, there exists the demand is non-negative. Natural. So last remark for today, that these requirements, of course, are satisfied by our function, by the division, by the what is it called? Proportional sharing. Because D is definitely a smooth market sharing mechanism. We have seen. Then a price and the pair as a function of your bit is indeed concave. It can be also shown. I think actually we have shown that. Yes, next step. Now, you can always get for any price and for any demand, you can get a bit that the demand will be exactly that. Simply beat the demand you would like to achieve times the price. And of course, the demand function is always one. So is definitely a generalization of what we've seen before. So next lesson we are going to talk a bit more about this requirement, and eventually formulate and prove that this our proportional division is indeed